Okay, so here we have an experimental question that deals with the motion of something that we drop. And so the first thing that I see when I look at a problem like this, I see the data we have relates distance and time. And so I would look at my AP equation sheet and see that I have a equation that involves those things. We know gravity is going to provide the constant acceleration, so this is accelerated motion. And I'd see the one that looks kind of like this. Actually, I'll write it a little bit more in the form the AP sheet has. Right, I'd see that one. And I recognize that this really kind of describes what my data table plots, right? Distance of fall is this thing. How far did you go at the end? And we know gravity causes an acceleration, and we know how much time we have. And these other things, actually I'll put in, right, this is d, this is negative g, right? And these other things, these terms, are, right, 0, because you're starting at rest, and you're starting at sort of your 0 position. Right, actually, this should be negative d, right, because you're going downward. So I recognize sort of what's involved in this equation from the data that I'm given in the description of the motion, that it's something that falls with a constant acceleration. And so I'm going to get the equation that d equals 1/2 g t squared. And now that I kind of know what equation describes the motion that we have and relates the data that I'm given, if I look at the graph, part A, I just have to put a nice smooth curve there, and it's pretty obvious what it is. And the data makes it pretty clear what's going on because of this, and the fact that the data, right, I'm going to try to reproduce the graph. The data is pretty, I think, already clear. This is the distance, and this is time. You have a point like, actually let's use a different color. You have a point like there, more like there, another one more like, kind of like there, and then one kind of like there, another one kind of like there, and then another one kind of like that. And so it's already kind of clear what shape it is. But the fact that I have this equation, this quadratic equation here, right, it's t squared, that's what I've boxed over there, tells me what shape I have to have, right? This is something like, if I rewrite it in a form you might be more familiar with in a math class, is y equals a x squared, right? A quadratic, where my y-axis is the distance and the x-axis is time. And so the smooth curve that fits that is just something that looks kind of like that. And that's all you really need. It doesn't need to be perfect, but it just has to kind of match and be curved, right? Clearly a quadratic shape. So part B is we're trying to relate these two variables, and we've already done most of the work, right? This equation is kind of most of the work for part B. What do we graph to make a linear relationship? So currently, because it's t squared, if we were to double t, we get a factor of 4 in the distance we travel, right? Because it's quadratic. We want to do something where we plot something else, where if we double that something else, we double the distance. That's a linear relationship, directly proportional. And again, this formula just tells you what it is already. If you want your formula to look like y equals mx, then all we need to do is kind of call a different thing x. So this is d equals 1/2 g, and then t squared, right? Where these are the sort of correspondences that we want. So what we want to really plot is d and t squared, right? Just what appears in the formula. Because if we do that, if we double the whole quantity t squared, we'll see that doubling this will lead to doubling d, and we'll get a linear relationship. So that's part B. You could also do the square root of both sides, right? That would be something that's consistent. You could have the square root of d and t as well, right? Just take the square root of both. That would work. You'd have a different slope, but it's still linear. Whichever one of those you pick, then part C is to make a graph. So I'm not going to do this perfectly, but I'm going to note a couple things. Let's say, I'm going to go saying that we picked the d and the t squared, because I think that's the more obvious of the two choices, because it's directly in the equation you have. So you're given coordinate axes with sort of tick marks, and nothing else. And so if you want to plot d versus t squared, you have to label, this is t squared, units of second squareds, d, units of meters, right? And then you have to put those values actually there. So if you square that time value in your data table, you have to plot the value 0.14 squared and put that in the proper spot. And the other thing you have to do, right, these tick marks are unlabeled, so you have to kind of figure out sort of the range that makes sense to use as much of the data space as you can, because you don't want to plot in just a tiny corner. So I see that if I was to square 0.63 seconds, I'm going to get a value around 0.4. So it makes sense to make each of these about 0.1 in spacing. And my distance goes from basically 0 to 2 meters. So I'd do this as like a 0.5. Something like that. And so once you've set up your coordinates, then it's just a matter of plugging in the values, which again I'm only going to kind of do approximately. That's one of the points. That's another point around there. Another point kind of around there. Another point about there. And then the last point right about there. And then drawing a straight line through it, because we've picked something to be a linear relationship, so we better have a straight line. Looks like we do, so something like that. And kind of as with all of these, since the mistakes you make in prior parts don't matter, all you have to do to get this to work is just whatever you pick in part B, plot it. And if you plot it correctly and label your axes correctly, you get all the points in part C, even if it doesn't actually work to solve the problem. For part D, we're told then to use the slope of the graph. So a good first step is to simply figure out the slope of the graph. Again, if your graph is wrong, that's fine, but it says use the slope, so you better measure the slope. That shows you have some clue at least what that is. So if you pick 2 points on your graph, right, kind of like that, you can calculate the slope, and it will be slightly different depending on exactly how you draw your line. But as long as it's consistent with the graph that you've done and the line you have there, you get the points. So for this graph, the slope is going to be found to be about 4.9 meters per second squared, with the values that I have there. But now we can go back to our equation where we have d equals 1/2 g t squared. But since we know what equation we plotted, we know there's a relationship between the slope and this 1/2 g, right? Those are the same thing in the equation. So we have 1/2 g is 4.9 meters per second squared, or g is, from that, 2 times 4.9, or about 9.8 meters per second squared. And so this part is the straight from the graph. Whatever you did, fine. Then you connect it to the equation and solve for g equals something. And again, as long as it's consistent, you get most of the points. But you definitely have to be able to determine the slope of the line. Now that one should be free points, even if you don't understand all the physics. Just draw a line and measure a slope. It tells you you need it. And then part E is now a more descriptive part. It's just state a way that you could improve the accuracy of the results and explain why it could improve the accuracy. So the key to this is doing both of those. If all you do is make a statement that's sort of generally true, something like, do it in a vacuum, that gets you 1 point out of 3 for this part. If you come up with something and then explain how it matters, you can get all 3 points. So, for example, you could say, do trials in a vacuum. There's your improvement. Now, why does that improve the accuracy? Well, because in free fall we assume gravity is the only force acting on it, and doing the experiment in a vacuum removes the effect of the air resistance force, thus making the acceleration of the object based only on gravity that we're trying to measure. That would be an explanation of how it improves the accuracy. Something else, you could say, you should do multiple trials. This would reduce the effect of slight timing errors when we stop our stopwatch by averaging them out. You could say we need to use a really heavy object. That would reduce the effect of air resistance relative to gravity and therefore make our results more closely measure just the effect of gravity. All those things all kind of work, but the key is you can't just list something. You have to say it and then explain why, what effect that change would have. And this is a substantial number of points in the problem, right? 3 out of 15 for this last part. And it doesn't really require any calculation as well, just sort of an experimental skill. But the key is don't be brief. Be as descriptive as you can be for what you want to do and why it would help. Both of those are necessary.